Okay, so today I'm going to be deriving the equation for centripetal acceleration, this one right here, that if you've taken ever a high school physics course or anything like that, or just any introductory mechanics course, you've probably seen this before. Now, I'm going to be doing so with a couple assumptions. I'm going to assume that the radius is constant, and I'm going to assume that the angular velocity is constant. And I'm going to be doing so by using Euler's identity, or not necessarily Euler's identity, but kind of a form of it, where you can express a vector on the coordinate plane using r times e to the I theta. And so I'm going to be using a position vector in the complex plane. But hopefully it'll kind of make sense in a second why I'm doing so. So if you think about the complex plane, you have your real axis, you have your imaginary axis. If I'm keeping my radius constant, that means the kind of range of motion, or the path, the allowed path that my particle or whatever I'm describing can follow, is just going to be a circle because it's at constant radius. And so that's how this corresponds to circular motion. So I'm going to start off with my position function, x equals re to the I theta, but I'm going to make a small adjustment. I'm going to say that x of t equals re to the I theta of t. And this makes sense. R is a constant, so it's not r of t, it's just r. And then theta is changing. I mean, a circle has a varying angle from, whatever horizontal of reference that you're using. So what I'm going to do now is I'm just going to take the derivative with respect to time to get velocity. So I'm going to say v of t equals dx by dt. And that's just the derivative of this with respect to time. So we can treat r as a constant and then just use the chain rule. So we can say this is, well, we take the derivative first. We say I, because that's in the exponential. So I r e to the I theta of t. And then we use the chain rule. We multiply by the derivative of the inside, which is going to be theta prime of t. And so that's our velocity. Next, I'm going to make a little substitution here. I see that I have re to the I theta of t in here. And so I'm just going to call that x. And I'm going to say that the velocity is equal to r, r's not in there. It's going to be I x of t theta prime of t. And then angular velocity, w, is just theta prime of t, so I can replace that with w. And I'm not going to write w of t because, as I already established earlier, w is a constant. Next, I'm going to find the acceleration by taking the derivative of the velocity. I'm going to say a of t equals dv dt, and that's just the derivative of this. Now, I can pull the I out of the derivative because it's just a constant. So I'm going to take the derivative of this using the product rule. So that's going to be I times x prime of t, which is going to be v of t, times w, plus, now I'm treating this as a constant, or I'm leaving that as it already is. I'm not taking the derivative of it. And I'm going to take the derivative of w with respect to t. But since w is a constant here, this right side of the equation goes to 0 because the derivative of a constant is 0. So now I have my formula for acceleration. A of t equals I v of t times w. I'm going to erase some of this stuff up here to make more room. And I'm going to rewrite this up here. I'm going to drop the t notation. I'm just going to write a instead of a of t. And same thing for the velocity. So I times v times w. Next, I'm going to find the magnitude of the acceleration, right? I'm turning a vector quantity now into a scalar quantity by taking the magnitude of this. So if I want the magnitude of A, or just A without the little vector sign on top of it, then I got the magnitude of I times V times W. And now I can kind of split this up. I can say that this is equal to the magnitude of I times the magnitude of V times W. Now I'm going to make a little substitution. We know that V equals R times W. So you can go from there and say that W is equal to V over R. So this becomes the magnitude of I times magnitude of this times magnitude of V over R. Now, obviously, since I'm taking the magnitude, I can just drop this vector sign on the V, the velocity. And then this right here is just V squared over R. And then the magnitude of I mean, if you think of what I really is, and I'll erase some of this stuff up here to make room, I is a complex vector, right? I is a vector in the complex plane. If you write down your real and imaginary axis, say 1, 2, right? Just writing down some coordinates. I is just a vector with length 1 on the imaginary axis, and so the magnitude of I is just 1. And so you are left with V squared over R. And so then you can write that the magnitude of the acceleration, or just A, equals V squared over R. And that's how you get this formula that you would see in an introductory mechanics class. Some people will prove this a little bit differently, geometrically, without using complex numbers. But I like to do it this way because I feel like it's really simple. It just comes from taking derivatives and switching up your coordinate system. But yeah, that's how you get A equals V squared over R using complex numbers. So it's easier to see.